Okay, looking at problem 222 now. And problem 222 reads, we've got a horizontal pipe, and it's got two sections, one 500 meter long section, and one 20 centimeter diameter, 700 meter long section. So I got a pipe that has two stages to it. So let's take a look at that. We'll say, let's call this the center line of the pipe. I think that's fair to say that we're going to have a center line. And then maybe that's our 700 meter there. That would be 20 centimeters. It goes from 10 to 20, right? So then we have a 10 centimeter section too. Okay. All right, so we said this here is 10 centimeters. This here is 20 centimeters. And then we have our length, which I think we want to say is going to be 500 and then 700. And 700 meters. Okay, so there's a pipe. What else do we know? We know that there's water coming out into the atmosphere over here. And it's the discharge rate, which we know as Q, is 0.01 meters cubed per second. I don't know if you can see that. That's here, 0.01 cubic meters per second. And it gives rates of energy loss. So the loss in this section is 0.01 meters per meter. All right, 0.01 meters per meter. So remembering that meter can be a unit of energy, it can also be a unit of length. So this is both of them. It's saying, although they still cancel, they're saying it loses a meter, or a 1/100th of a meter of energy for every meter that it goes. Okay, so it's technically unitless. And then the loss in this section is, I believe it's a little bit more at a little less, quite a bit less, 0.002 meters per meter, which makes sense. You know, with a bigger pipe, you have more surface area and, more cross-sectional area relative to how much surface area it has. And the surface area is where the losses happen typically due to the friction. Okay. So what we want to find out is what is the required energy going in, right? E inlet, question mark. Okay, so what is the required energy going into this thing? Well, this is not a real difficult problem. We're going to say that we've got E, which is our energy, and we'll do Bernoulli's again, and we've got V squared over 2G, and we have, that's our kinetic energy, and then our pressure energy, P over gamma, plus Y. Okay, it says it's a horizontal pipe. So Y is not going to change it anywhere along the pipe. So that one cancels. Okay. The other thing is we need to know what's going on at the inlet, and then we only know what's really going on at the outlet. Other than the discharge rate is going to be the same throughout here, but we don't know what the pressure is, what's going on with the pressure. So we do know that we can figure out the velocity as this thing is exiting is going to be Q over A. So we could say V outlet is Q over A. A for this section of the pipe, A over here, is going to be pi over 4 times 0.2 meters squared. And we know what Q is, so that's 0.01 meters cubed per second divided by pi over 4 times 0.2 meters squared. Okay, you can solve for that. And it also says that it ejects out into the atmosphere. So this is the atmosphere. What that means to you is the gauge pressure goes away. Okay, so here we can say the energy of the outlet is just going to be the velocity energy, just the kinetic energy, because it'll have the potential energy as well, but the potential energy right at the outlet is going to be the same as the inlet, so there's no difference there. So the energy we're going to have to put into the inlet is going to have to equal the energy at the outlet plus the losses. Okay, so I've given you the V, and the energy of the outlet is going to just be V outlet squared over 2G plus the losses. What do we know about the losses? Well, we got 0.01 meter per meter, 0.01 meter per meter, times 500 meters, right? 0.01, whoops. So that's the loss in the section 1, and then section 2 is going to be 0.002 meters per meter times 700 meters. Okay. So yeah, that doesn't leave you much to do there, but that shows you how it's done. And yeah, make sure you put that in engineering submittal format, and you are welcome.